How's everybody doing? Professor Bryant back with another installment of Workout Wednesday. I've gotten some questions about stoichiometry, balancing equations, and particularly looking at incorporation of enthalpy into some of the stoichiometry problems. So that's what we're going to try to do here. So um, when we're talking combustion, which is a pretty common type of problem that we see, I wanted to look at writing a formula for combustion of a carbohydrate and balancing it, right? Because a lot of students are having issues with just getting this part done, and this should not be where our students are stumbling. So, combustion reaction, as soon as we hear that, we should be thinking burning in oxygen, right? Burning in oxygen. So, if we rewrite our reactant, which is sucrose, a carbohydrate. Why is it carbohydrate? Because we got carbons and hydrogen. And we burning it in oxygen. We should get CO2 as a gas plus water. And that is as a gas as well. Okay? So here we have the chemical equation, but it is not balanced. So there are numerous different ways. If you watch a bunch of different videos, there is a plethora, again, of different ways to balance chemical reactions. What I like to do when we talk about combustion specifically is I like to balance the number of carbons first and determine if we will be able to utilize an odd number of oxygens on both sides. Now, what do I mean by that? Well, if we take a look here, this subscript of 12 is 12 atoms of carbon in this molecule, and that is effectively 12 atoms that we must have on the other side, right? We must have on the other side. The number in front represents the number of moles of that molecule that is used up in the chemical reaction. So if we want to have 12 moles of carbon that only come from this molecule, they only come from one place. To get 12 over here, since this is a multiplication situation, we need 12 CO2 molecules. We need 12 moles of CO2. Hopefully we see that this 12 is effectively being multiplied by the 1 that is not written here but is assumed to be here. 12 times 1 gives us 12, and here we have an assumed 1 where 1 times 12 gives us 12. Now, you can write a table. You may see a bunch of different other methods to balance this, but the carbons are currently balanced, okay? The next thing that you should do is you should balance hydrogen. The reason why we are okay with balancing carbon first and then hydrogen second is because there's an odd number of oxygens here, an even number of oxygens here, where there is an odd number of oxygens in water and an even number here. So we won't have an issue going back with creating an odd number on the right side. So we want to look at hydrogen, and we see that we have 22 hydrogens here and we only have 2 here. Since we need to get a whole number here that multiplied by 2 will give us 22 to have our hydrogens balanced, we need an 11 over here. So now we have not only carbons balanced, but we have hydrogens balanced. Now we need to balance oxygens, and if we look, we have 13 oxygens on this side currently, and over here we have 12 times 2, which is 24 oxygens. Again, this is a multiplication. And then we have 11 times 1. So we got 12 times 2 is 24 plus 11, right? That's 35. 24 plus 11 is 35. So to get 35 over here, we have to get 24 oxygens here. And to get 24 oxygens here, we need a 12. Okay, so 12 times 2, 24. 1 times 11, 11. 24 plus 11 is 35. And we do the same thing over here, 35. So that is the balancing. I am not utilizing some grand schematic. I'm utilizing a little, just some basic multiplication, mathematical understanding. Okay. Now, the second thing that I would ask you to do is to do some stoichiometry. So let's say you wanted to determine grams of oxygen consumed, very important word here, grams of oxygen consumed if 0.25 moles of C12H22O11, let's make sure that's in the window, were burned. Now, a lot of students get a little concerned here. They get fearful here because they're not necessarily sure what these words, this vocabulary mean. Okay, first off, grams means we're dealing with mass, right? And they want the mass of oxygen. Consumed means that we are, it means that this forward reaction is taking place. And we are giving a theoretical amount if, that's why we use the word if, 0.25 moles were burned, meaning if we burned up exactly 0.25 moles of this carbohydrate, how much oxygen will we need? That's what this problem says. It just says it in a different language. So don't let the language concern you. Learn the language. And then that makes the problems much easier. From here, we are being given an amount and we need to convert using stoichiometry and the balanced chemical equation to determine grams of oxygen consumed, also dimensional analysis and conversion factors. So we will start with what we were given, 0.25 moles C12H22O11, 1 mole of C12H22O11 for every 12 moles of O2. Now, this first step in this first conversion factor, where does this come from? A lot of people are confused on this very first step, and it'll be very difficult to get the right answer if you're confused on the first step. This conversion factor, this ratio, it comes from the balanced chemical equation. It comes from this 12 to 1, 12 to 1. Why is oxygen on the top? Another question I get a lot. Oxygen is on the top is because we are converting to try to figure out grams of O2. So O2 is what we are trying to get the answer for. So we need to cancel away from the unit or the type of moles of molecules that we were dealing with, and we need to move towards the moles of the molecule that we're interested in. That is why, remember, the unit and the type of molecule is canceled when we're dealing diagonally. Okay, but we have been asked about grams and not moles, so the problem does not stop here. We can then add another conversion factor where 1 mole of O2 is equal to 32 grams of O2. This is an equivalence, right? That's what each of these vertical bars, what happens in between there, this mathematical ratio must be equivalent, not equal, equivalent. 32 grams, where did that number come from? It's not in our problem. 32 grams is the molecular weight or the molar mass of oxygen, 16 plus 16. That's where we get this from. 16 comes from the periodic table. 32 is 2 times 16. All of our dimensional analysis is complete. Now we just need to go to the calculator, 0.25 times 12 times 32. And this number is 96 moles excuse me, not moles. Sorry, 96 grams of O2. We have canceled out the units, and you can verify that by looking 12 moles of O2 gone, moles of sugar gone. We're left with 96 grams of oxygen is what is consumed, okay? What is consumed. Okay, now let's talk about energy, okay? A lot of times you will see this particular chemical equation with a delta H with a little circle, and this delta H is enthalpy. It says how much energy is created or how much energy is released when we burn this sugar. Now realize this particular sugar is a carbohydrate. This is C12H22O11, but each sugar is different. Each sugar will have a different delta H because it has a different amount of bonds that are broken. The actual value for this for sucrose is negative 5647 kilojoules, negative 5647, and this is kilojoules per mole. Okay? Kilojoules per mole. Now, what does the negative sign stand for? The negative sign in this case says that this is exothermic, right? Exothermic. But it should make some kind of intuitive sense to us that when we burn something, heat is released. That's the reason why if you burn yourself, you get anywhere near a fire, heat is released. And it should make some intuitive sense. So how does this value incorporate with our stoichiometry? So the next question that we could ask ourselves here is, how much energy released? So if we were to burn 0.25 moles of our sugar, how much energy is released? Well, energy is directly related to the balanced chemical equation, and it can be placed in the stoichiometric dimensional analysis the exact same way that we did up here. So we have a value, and I'm going to rewrite this so you can see it. Negative 5647 kilojoules per mole. And if we have been given 0.25 moles of C12H22O11, we have a conversion factor that is directly related to moles, and 1 mole of C12H22O11 is negative 5647 kilojoules. Remember, kilojoules is an energy unit. Kilojoules per mole gives us the ability to cancel, and we are left with a unit of energy that we're interested in, 0.25 times negative 5647, which is negative 1411. Negative 1411.75 kilojoules of energy released if we burn that many moles. Now, remember, these problems can get more complex when you start incorporating mass to mole conversion, reactant to product conversion. But since enthalpy is effectively a product, you can always utilize stoichiometric coefficients and plug this into dimensional analysis and find out how much energy was released, period, if you know how much of the fuel, in this case the carbohydrate, was burned. Again, if you have any questions or want to see some more examples like this, I'm going to zoom out so you can take a look at it. Please leave a comment or send me an email, and I look forward to hearing from you.